Hi, so I'm presenting the duck is cold question. So you have a duck is cold and is sitting on a heating cushion. Suppose the bottom of the duck is modeled by the paraboloid insert equation. The temperature is given by that equation, and the heat flow is F equals negative K, the gradient of T, where the positive constant K is the conductivity of the duck's feathers. What is the heat flux towards the duck along his bottom? So we're going to use the flux integral for that, and that has the form shown below. So in order to approach this problem, we want to start by finding the surface, which is the duck's bottom. So the duck is represented by elliptic paraboloid, which can be seen on the duck in the corner. But this is represented by the equation x squared plus y squared minus z minus 2 equals 0. And this has the bounds x squared plus y squared is less than or equal to 1. So we can rearrange this first equation in order to get z equals x squared plus y squared minus 2. And this is really useful because from there we can get the r vector that was used in the previous slide. So you get x, y, and then you substitute our z equation in there. So everything's in terms of x and y now. So this is going to be the surface that the field is going to be exposed to and how the field is going to interact with the surface. And also this is going to be the bounds of the dx integral from the previous slide, from that equation that we have. So the bounds are going to follow the x squared plus y squared is less than or equal to 1 equation. So then you can solve for the bounds of x, which is the negative square root 1 minus y squared is less than or equal to x, which is less than or equal to positive the square root of 1 minus y squared. So now we want to find our field, which is going to be the heat gradient. It's given in the question as F equals negative K, gradient of T. So we take the gradient of T, so that's just taking the partial derivatives of T at various points, and then we turn that into a vector, and we multiply that by negative K. So that gets us our field, So the flux integral becomes, you can substitute in our F into the equation we had on the originally. So you get negative K, and then you get the flux integral, but you have, instead of your F, you have the gradient of T, and then you have your surface. So now we want to find our ds. So we're going in, so we're going to find so we have our surface already, we figured that out a while ago. So that's x squared plus y squared minus 2. So now we need to find our, the cross product of the derivative with respect to x and the derivative the derivative of the vector with respect to y, and that's going to be dx dy times dx dy. So if you can see, you have when you take the cross product of the vector of the two partial derivatives of each vector with respect to x and y, you get minus f of the partial of f with respect to x and minus the partial of f with respect to y. Sorry, that's a tongue twister. So that's because when you're solving the x, when you're solving the partial derivative of the vector with respect to y, if you just have, for example, the first part of the vector, the x, just the x before you enter the comma y, the partial derivative of that with respect to y is just going to be 0. So that's why you get this form that that's shown here. So when you take the partial derivative of f with respect to x and negative partial derivative f with respect to y, you get the vector that's shown there. So your ds is really just this vector, which is negative 2x, negative 2y, 1, and that's multiplied by dx dy. So that's your new ds for the flux equation. So now that we have all the parts that we need, we're going to actually take these two and substitute it into the modified flux that we saw earlier, which is the K times the gradient of T, integral gradient T ds. So we have our ds and we have our gradient T, so we're going to take the dot product of our r sub x and then r sub y cross product. So there we take the dot product, we find an integral in terms of x, y, and z, but we don't have a dz component. We're integrating in terms of x and y, so we substitute in our equation for the bottom of the duck, which is z equals x squared plus y squared minus 2. So we substitute that in for z, so we find everything in terms of x and y, since that's what we're integrating in terms of. And also all of our bounds for the integral were found when we were finding our duck surface.
So now we're really starting to solve our integral here. And if you look at the highlighted part, that really can be solved well using polar coordinates, because polar coordinates are governed, like the conversion from polar coordinates, from Cartesian to polar, are x squared plus y squared equals r squared. So you can substitute that part of the integral in for r squared, and then 1 minus y squared, those bounds are also represented by just 0 to 1 in R. So because that's well represented by polar, we have this, we're really able to simplify this equation and end up with the below integral, which is easier to solve. So now that we have our simplified integral in polar coordinates, we're able to go in and take the double integral first with respect to r and then with respect to theta. So when we take it with respect to r, we have the bound 0 to 1. So we integrate with respect to r, take those bounds. Then we integrate with respect to theta after we solve the integral for r, and we get we also have to multiply by that 2k that we factored out earlier. That represents, the k represents the temperature, and 2 is just factored out. So now we have 5 pi k as our final solution.